All right, so I'll be telling you about why do we need to be careful about updating the software that we have in voltage regulation, the software that we have in the smart grids. So Marcus have given us a very good overview of why, ensuring that when you incorporate solar and wind panels into your smart grid is a very important thing to ensure that you still have the service quality that you provide to the customers. So what we have here is, I will tell you about what can go wrong and what we have been doing in KTH in resolving this problem. So renewable resources such as solar panels and wind has been used in households, and the fact that they're in these households changes the traditional structure that we have in the power grids. So for instance, on a sunny day, you would have that particular household will be a power producer, and otherwise on a day like this, it would probably be a consumer. So this causes fluctuation in the voltages in this power grid. And what we want to ensure is that the voltage level that we provide to each of these customers remain within a safety margin at all times. So as a result, to ensure that this happens, we have energy management systems that sit in each of these households. And these management systems would then regulate the voltage level in each household. So due to the changes in the distribution network, so for instance, if we add another household to our power distribution grid, it would change the properties of that particular power network. And this requires the software to be changed, to be updated over time. And to ensure that, but then we have to be very careful in how we actually update this particular software. For instance, there are two particular failure scenarios that we can, that I would provide an example for. So for instance, if you updated and you failed to actually update that particular software in that particular household, then the local controller would fail, and the software may slow down after an update. And for instance, you could also provide the wrong reference voltage to each of these households. And as a result of that, the voltages that are provided to each of these households here may exceed the safety limit that's being specified, and that's not a good thing. So with our project partners, with the AIT and Siemens, who are in Austria, and office in Fraunhofer in Germany, we here in KTH concentrate on using control theory to develop protocols for the secure rollout of software in regulating the voltages. By secure rollout, I mean by actually ensuring that the voltages remain within a safety margin, and whenever we update that software. So let's look at a particular setup that we have been studying. So here I've provided a low voltage residential power grid. Here you have, it's not very clear, but I'll point out what they are. So this here is a substation, and this is connected to the medium voltage distribution network. Here we have 3 households and perhaps many more that are connected to this power distribution network. And here, the setup is as follows. So we'll provide this substation here is the brain of this power distribution network, and it provides a reference voltage to each of these households here. And there's a tap changer that regulates what the voltage is at the head of this distribution network, and this connects to the medium voltage distribution network. Here we have the 400-volt line-to-line residential subnetwork. So the software, so what happens here is that the brain then provides a reference voltage to each of these households, and the software is then required to follow this particular reference voltage. But then because of how this grid is connected in this particular sequential way, households that lie perhaps further down the grid would have a lower voltage than, say, the one at the head of the grid. And also because these households could be consumers or producers, depending on the weather. So the voltages may not always lie within the safety margin that is specified by the operator. So So here in KTH, we have developed a software, an energy management system, the software that sits in that particular system that can roughly be described as follows. It's a lot more involved than that, but it really involves, really I can narrow it down to this particular function that I've drawn up here. So let me explain what they are. So the x-axis is the difference between the voltage at each of the household to the reference voltage. And this y-axis here is how much reactive power each of these households would inject into the grid. And this reactive power controls the voltage of each of these households at the point of connection to the distribution grid. So when there's no difference between the voltage of the households to the reference voltage, then we do not inject any sort of reactive power. But then if there's a difference, if there's a big difference, we'll then inject a reactive power. And also, of course, the software then decides how much to inject, so there's a saturation point here, and also when to actually start injecting. So here we have a dead zone to prevent any sort of unwanted behaviors. So let me provide a scenario in which if we do not update this software properly, what can possibly go wrong? So let's have a look at this particular scenario here where we have two customers. So let me be very clear about what line represents what. So here the green dashed line represents the safety margin in which we have to ensure all the voltages lie within. And the blue line is the voltage at the head of the distribution line. And the red line is the voltage of this customer, of customer 1. And the orange line here is the voltage of customer number 2. So at this particular point here, say for instance, there's a failure in the update of this software, so now it has been flipped. So imagine that this, this particular function here has flipped in its horizontal axis. So now if the difference, so now it would inject maximum reactive power when the difference is in this particular range. So if that happens, then the voltage of customer 1 would start increasing. But then it starts increasing, but that's still okay. It's still within the safety margin that we've specified. But then consider, for instance, now there's another failure in the software of customer 1, and then which is the flip of this particular function. Then it pushes the voltage of customer 2 all the way up and away outside the safety margin. So here, this bit here is an undesirable condition whereby the voltage actually lies outside the safety margin that the operator has specified. It eventually goes back down within the safety margin, but this particular time period here is very undesirable. So what can we do? In our setup, we have the substation, which is the brain of this particular sub-network. It gives some sort of rule to our reactive power control. So that's the energy management system that sits within all the households. So it provides the voltage reference to it, and then this then actuates, and then and we have sensors that measures the voltage at each of the connection points, and the PV, the photovoltaic cell inverter, then injects and decides based on the software that I've just shown earlier, which then curtails the injection of power and which influences the voltage at each connection point. So we have tested this on a benchmark by the Seagrid Task Force. And what I've shown here is a European residential network whereby, well, you have different households. So all these are loads here. So we have R17 and R15, which are households. And this can be rewritten in the particular frame setup that we had before. And at KTH, we have devised a set of rules to check that the software does not lead to failure, as I have explained a while ago. And the rule basically boils down to the fact that the this function has to lie within this particular yellow region. And if it lies outside that particular region, we'll have voltages that exceed the safety margin that we have specified. And so because I'm running out of time, so I'm going to go on and summarize what we have done. So power grids are the renewables, with renewable resources are the future, but we have to be very careful in how we actually update the software that, that manages the voltage manages how we actually regulate the voltage in each of these power grids. In KTH, we have used control theoretic tools to design secure protocols for software rollouts. And we're in the process of testing these protocols on the test bed with the hardware that's available with our partners in Austria. There's the AIT Smartest Lab. So thank you very much, and I hope that there'll be a lot more discussions later on.